My name is David Sackstein. I'm a freelance programmer and an instructor. I am personally quite fascinated with the fact that in the last 10 years or so, C++ has gone through a revolution and has really become a cutting-edge modern language. We can do wonderful things that we could never do before. Today, I'd like to talk to you about threads, coroutines, and fibers. Threads are very well known. Coroutines are all the rage. There are quite a number of talks in this conference about coroutines. Fibers are less well known. And I would like to try to convince you that you can boost your program's health by adding fibers to your coroutine. So the agenda for today is as follows. I'd like to start with an overview of coroutines and to discuss two high-level implementations, the stackless and the stackful. These two implementations are similar in the way they are used, but there are subtle differences. And we're going to be discussing the Coroutine TS and Boost Coroutine 2. Then we're going to talk about specific use cases. One is generators, it's a family of use cases, and asynchronous APIs. The asynchronous APIs will lead us on to talk about threads and how threads are used or should not be used for asynchronous APIs, and then how fibers can help with some of the problems that we have with threads. And then we will talk about the Boost fiber library itself. I'll show you a few examples of how it can be used. As I mentioned in the abstract, it is actually very convenient to use the Boost library because the semantics of many of the objects that you will find there are very similar to those of the stood thread APIs. And then we're going to go through a series of demonstrations, basically a series of projects, in which I'm going to demonstrate the use of threads for asynchronous API, followed by the use of asynchronous IO without threads, followed by implementation of coroutines, and I'll make mention of using coroutines from Boost and coroutines from the Coroutines TS, and finally to see how we can actually use fibers in that project. And in the conclusion, I would like to talk a little bit about when it is useful to use coroutines and when it would be more useful to use fibers. You can imagine already that the use of threads will not be advised, at least when we're using asynchronous IO. I mean, threads are not, it's not they're not to be used, but they're to be used in a specific way in combination with either coroutines or with fibers. So we'll talk about the differences between all of those technologies. And finally, hopefully there'll be time for questions and a quick summary. If there are questions during the presentation, feel free to ask. I may ask you to postpone the question or to the answer to the end because we are fairly short for time. Before I begin, I would like to thank Oliver Kowalski and Nat Goodspeed, who both assisted me in preparing for this presentation, answered numerous questions on email, and they are a great source of information. Oliver is the author of the Boost Context, the Boost Coroutines, and the Boost Fiber libraries. And Nat Goodspeed has been a contributor to these libraries, and he's also an author of a number of proposals to the CPP Standardization Committee for fibers and for coroutines. He is also a very enthusiastic speaker about these technologies, and he speaks CPP Now and CppCon. I'll mention some of the examples that Nat provides during the presentation. Okay, so more information you can find. I would recommend the best source of information actually is the Boost Fiber documentation and the Boost Coroutines documentation. There are lots of examples there, and the tutorials are excellent. But in addition, you can see the code behind the slides at this location that I've posted on GitHub. I hope it's available now, and if not, I'll make sure it is after the talk. And you can, of course, contact me at this email. Comments on the presentation, questions, all are welcome. So let's begin with coroutines. Everyone knows the definition of the coroutine. Coroutines are generalizations of subroutines. Unlike subroutines, they can be suspended and they can be resumed. And when they are resumed with the same execution state with which they were suspended. That means they'll be resumed at the point of suspension, and any local variables that were originally present and alive remain alive and in the same state when the coroutine is suspended. And maybe an important other feature, which is important to mention, is the fact that the objects that are created on the stack in the coroutine are only disposed of using the RAII pattern when the final return from the coroutine occurs. So in a way, a coroutine looks like a function, but what's happening behind the scenes is suspension and resume. And the use cases for coroutines that I want to talk about here are generators and parsers. I will mention briefly pulling from visitors as one of the examples. And the second pattern is the asynchronous APIs. That will be the focus of most of our discussion. Asynchronous APIs free of callbacks. And then, of course, there are combinations of the above. There is such thing as an asynchronous generator, which generates sequences of information, but some of those or all of those are themselves awaited upon as they are asynchronous. What is common to all of the above? And this helped me understand what coroutines are all about. What is common to all of these patterns, different as they may seem, is that they help us invert control. We allow code that is typically governed or dominated by callbacks to be combined with the initiating functions and to look together as if they are one function. And that is really what inversion of control is all about. If we take, for instance, the generator pattern, within the generator we have the pattern is basically a producer of information, a sequence of information, and a consumer. The problem is that the producer and the consumer both want to be in the driving seat. The producer wants to run a function, update its state, generate some information, and send it out using a function call. A callback, for instance, or a function call. It doesn't like to be called back for more information each time, because if it's being called back, it needs to restore its state. It needs to store state, restore its state, and continue from where it left off. That's not a very convenient programming model for the producer. But on the other hand, the consumer has the same interest. The consumer is doing its own thing, and then from time to time, it needs to get hold of some information, so it would like to make a function call to call upon the producer to provide that information. So what we have here is a conflict of interest. One of them wants to pull, one of them wants to push, and both of them want to do it by a function call. How can a function call behave both as a push and as a pull? And the answer is a generator, which can be implemented using coroutines. We will see later on that a similar pattern arises out of the requirement to make asynchronous APIs simpler. Okay, so we have two implementations of coroutines that I'm going to talk about here. One is the Coroutine DS, which is in the process of being standardized. And the other is Boost Coroutine 2. Boost Coroutine 2, actually, Boost Coroutine has been upgraded and now is deprecated. I recommend you use Boost Coroutine 2, which has a similar API with some limitations. The difference between these two implementations, I won't go into the details of the implementation, but what I would like to say, because it is important for the usage patterns, is that the Coroutines TS takes the stackless approach. And another way of saying that, or an implication of that, is that it suspends by return. What happens is, when you enter a coroutine, behind the scenes, the compiler is generating a representation of the state of the coroutine and passing it back in what we call a future-like object to the caller. And the caller needs to be aware of the fact that this future-like object could either represent a result or a potential result, which may eventually be an exception or it could be an actual result. On the other hand, so this is what we call suspend by return, because when we suspend, we rely on the fact that the information of the state is passed back to the caller, and there is an interaction between the caller and the coroutine using this state. On the other hand, Boost Coroutine 2 uses a stackful approach. What actually happens is we allocate a stack for the use of the coroutine, which allows the coroutine to run, as it were, as a regular function, calling other functions and so on. And the suspend is by call. At any point within that coroutine, either in the function or in a nested function that it calls, the coroutine can suspend. When we use stacks, suspension means we are doing a context switch. So the processor is running one stack. Suddenly it is switched away and it moves to another stack. The same thread continues to run on a separate stack, which is basically the state of the execution. But that can operate at any level. It can be called from within a nested function or a nested function. It doesn't have to be called by the top level with a special keyword. And this has implications which we will discuss in just a moment because I want to focus on the use cases. Let's talk about generators and see how they are implemented, how they're used in both of these implementations, both in the Boost and in the Coroutine TS. So here is a typical generator using Boost Coroutine 2. Now this may not be similar, this may not be well known to all of you because we're all concentrating on the Coroutines TS, but I think you'll find that it's very similar. What you see here is, first of all, in order to use the Boost Coroutines, you need to include the headers. You can use all.hpp, which includes all the relevant headers for convenience. And I've also added here two template aliases so that I can use pull type and push type. These are asymmetric coroutines. So there is a puller and there is a pusher and there is a particular relationship between them. They both have roles. What I'm creating here is the pull type. The function generate integers calls the pull type, creates a pull type, and the pull type is our generator. To create this object, we call a constructor, as you can see, which takes a lambda, a callable object. And the callable object takes by reference an implicitly created sync object or push type object. And when I say implicitly created, you don't have to create it. It is created for you. You can use it within your callable function to yield control and to provide data outwards towards the pull type. So all of that boilerplate code is done for you. What you really need to concentrate is on what goes on inside that lambda. You have a sync, which you can invoke, you can push, just like a function call. And this is where inversion of control has worked. From inside the generator, the consumer has its own state within this callable object, and it uses the sync object to push data rather than have to be called back all the time. So it feels it's in control. What actually is happening is that sync object is generating down under a suspension of this stack and a context switch to another stack, which basically is the caller at the consumer side. Okay? So this is how it's done with Boost Coroutines 2. With the Coroutine TS, slightly shorter syntax, in order to use Coroutine TS today as it's in experimental stage within Visual Studio 2017, you have to include a switch, the /await in your command line, and make the appropriate includes, which are currently under the experimental namespace. So I've included here experimental generator, which is one of the patterns within that space. And here again, I've used a template alias to make use of the generator easier. The generator is an object that is provided for you. All you need to do is invoke the co-yield keyword. The Coroutine TS defines three keywords, three new keywords for the language: co-yield, co-return, and co-await. I won't discuss them all here. I'm going to mention co-await later on. For the moment, as we're discussing generators, co-yield is sufficient. So this is a generator. Now, I want to point out something here about the objects that we are creating and that we are using. Which of these objects that we've seen are actually first-class objects? Can they be passed around by reference, by address? And the answer is that for both implementations, the generator is a first-class object. You can pass it around, and for as long as it is alive, you can pass around references to it fairly easily. This enables you to chain generators. So here is a chained generator using the Boost Coroutine library. Here we have a new generator called generate squares, using the same pattern, again, whereby it creates an object that takes a lambda. And that lambda, as you can see, takes an implicitly created sync object, which is a push type. But you can also see that it can take by reference, it can capture by reference, a parameter that was passed in, which is another generator. Generators in Boost Coroutine are pull types. So that another source could be, for instance, the result of the previous call that I made to generate integers. And I can use it freely inside the generator, the new generator. I can iterate over it. And then I can finally call the sync object, which is how I communicate with my caller. Similarly, we can do the same with the Coroutine TS. The generator is an object. We can pass it in by reference, and we can chain generators in this way. Again, we have to use the co-yield keyword. So the generator itself is a first-class object. But what about that sync object, the thing that we are pushing? is that a first-class object? Can that be passed around by reference during the life of the coroutine? And here, there is a difference between the two implementations. When you're using Boost Coroutine 2, you receive that object by reference, which is the sync object. You can then pass that along to a nested function, as long as you're still within the scope of your Lambda where it is alive. You can make further calls passing in that sync object. Any nested call can then take that sync object and push outwards any data it wants to create. So you can create nested generators from within generators very easily. However, unfortunately, with the stackless implementation that we're adopting for coroutines in C++, here is the limitation. If you want to generate from within a nested function, you need to call co-await in that nested function. To call co-await in a nested function means that that function itself must be a coroutine. And therefore, your coroutine needs to communicate like with a coroutine. Typically, what you will find is that if you have nested generation, you'll have to iterate over a nested generator. And this pattern is common for instance, the Python iterators, and in C# when you use yield, you also cannot yield from an inner function. You have to create a new enumerable and iterate in the outer function, over the enumerable generated by the inner one. So this is a small limitation, and it's important to understand when you're selecting the technology that you need. Okay? So this is what you can do with Boost Coroutine 2. It's a very simple example, but it does demonstrate the point. If you have your coroutine called generate squares, and you find that it's quite complex and there are lots of loops there, and you would like to somehow or other extract functions to make it more simple. What I've done here is shown that I can extract a method which actually does the internal loop. And all I need to do to make that happen is to pass in by reference the sync object, and then iterate over that internally. Call that internally inside the nested loop. This is something that you will not be able to do with resumable functions in the standard unless this extracted method is itself a coroutine, and then you have to loop over it in the outer function.
Question?
Yeah.
What is the extracted method returning?
It itself, you're right. As it so happens, it doesn't need to return that. This is an important point. Yes, it's actually a mistake. This was actually my point, and I'm glad you pointed it out. The extracted method doesn't need to return anything. Right? It's sufficient for it to be a nested call and to make calls into the sync object. Thank you very much. So let's talk about the implications of the stackless and the stackful. Okay? A resumable function which is stackless, as the coroutine TS is proposing, requires much less memory on initial call. You're not allocating a stack. You're allocating only enough information to capture the state of that function that is the body of the coroutine. In some cases, as Gore has demonstrated in numerous articles and in his talks, that heap allocation can be elided, and it can even be made a stack allocation. And in some cases, when the compiler can see all of the code of generator and producer, it can actually inline all of the code, and the coroutine disappears. So you have optimizations that are possible, especially with the advanced compilers that will adopt this feature, that are not possible or much more difficult to implement maybe with a stackful coroutine. However, the limitation is that when generators are nested iterations are required. That's something we've just seen. And as they suspend by return, just a second ago, all functions that invoke a coroutine must be aware that the caller may suspend. And that's another point that I'd like to make about the differences between the two. Yes?
For a library, it contains a recursive generator which allows to yield from the bottom generator. So you don't have to have necessary iterations.
Okay, I haven't seen that, and I'll take a look. Thank you very much. So what Gore is pointing out is that it is possible to do nested generation without necessarily creating a new coroutine. Is that what you're saying? Okay, I'll certainly take a look at that. The second point that I'd like to make about the differences are the fact that when you use stackful coroutines, you are actually creating a function which looks like any other function. And therefore, when you're integrating with a third-party library where you don't control the code, you have much more option, or it's much easier to make that integration. Now, Nat Goodspeed has two examples for this. One example he provides in his C++ Now 2016 talk called Pulling Visitors. Another example is on the Boost Coroutine library documentation, which I will mention here. It's simpler to explain. But they are examples of a similar feature. So the example is parsing XML with the SAX, the Sax API. As you all know, if you're reading XML and you want to stream that XML, you don't want to read in the whole XML object in order to see the first node. And the way you can achieve that is by using Sax. What you do is, typically in all the implementations, you provide callbacks for each of the different nodes, if you're interested in them. Then you make an invocation to Sax to pass the XML from a string or from some stream. And then it calls back into your functions, and then you get callbacks on each of those nodes. But what happens if you want to iterate recursively over those nodes? That's not something that's easy to do without coroutines, and this is precisely an inversion of control that coroutines can give us. So what we would like to do is we'd like to create a generator of nodes, which I can iterate over in an efficient way, while still using the Sax API. The Sax API does not know about coroutines. So the callback that you provide cannot be something that looks any other than the signature provided by the Sax library. It doesn't return a future object or anything that looks like a future object. And therefore, to integrate with that Sax parser, you need somehow or other to do something that doesn't look like a coroutine. Considering the fact that the Boost coroutines allow you to pass around the sync object, you could actually store that sync object, or the address of that sync object, in your own class during the lifetime of the lambda that you provided to your coroutine. And then at any point, including in the callback, you can reference that sync object and use it to push data out. You don't need to sign in any way that function, that callback, to be a coroutine. It's a regular function. So from that point of view, it's much more straightforward to take an existing framework that uses callbacks and convert that into a coroutine-enabled API. Okay. If, of course, you control the code, no problem at all. You can actually make each of those callbacks generalized and make them coroutines, and then you can invoke them as coroutines. So there's another example, as I said, of pulling pulling visitors from Boost Graph, but the idea is the same. So that is the generator pattern. We've demonstrated how that does an inversion of control. Now I'd like to talk about asynchronous I/O and how asynchronous I/O can benefit from coroutines. The next step is to talk about threads and fibers, okay? But we're still on coroutines at the moment. So when I mention asynchronous I/O, maybe it's a figure of speech. What I really mean is any operation that requires a wait, something that I can't do anything about, but I have to wait for. And as we know in multitasking programming, it is not a good idea to block on such a wait, especially not to spin lock, if it's going to take some time. What you prefer to do is to use an asynchronous API, if that's provided, which essentially allows you to invoke an initiating function and provide the callback, and then the callback is then invoked when the operation is complete. The problem with that is that you get a chain of callbacks, and your callback and your logic, your business logic, is now split up into disjoint callback functions. And furthermore, error handling can be fairly difficult. Depending on how it's managed, you have to think about the fact that the last callback that is mentioned in the chain, that is invoked in the chain, cannot throw an exception necessarily or simply, because the stack in which it lives is not the same stack in which the original initiating function was invoked. So the initiating function can no longer see that exception in the normal way. And there are many ways to go around that. And of course, this can be managed. If you have good code reviews and you do a lot of testing, you can make sure that this will work for you. And this is how things have been done for many years. Asynchronous IOs are not a new art, but they have been difficult to implement. We would like to have this initiation and callback turn into something that looks like a function call. And again, we have a similar situation to a coroutine. We would like to be able to instantiate the function as if it was a synchronous call, and then continue with the callback. Not have to provide the callback that will be invoked later, but to actually continue in the same stack, or what looks like the same stack. So this is again a problem of inversion control, and it's a classic scenario where we can benefit from coroutines. What's interesting about this particular scenario, and it's different from generators, is that the callback is not necessarily being called or invoked by the consumer. In the case of a generator, I didn't go into the pattern itself, but the interaction between suspend and resume occurs between the consumer of the generator and the caller, and the implementer. In this case, the initial call is made by the caller, it generates the call, but the callback may actually be implemented, may be called back from another thread, some thread pool object, which is now being handling a completion. But that doesn't change the fact that we can use coroutines to invert the control and make our coroutine look like a synchronous function. So in order to demonstrate that, I'm going to make a short detour and talk a little bit about Boost.Asio, because Boost.Asio is really a state-of-the-art library for asynchronous I/O in C++. I think it's even been discussed to be proposed to be part of the C++ standard. Of course, it implements a particular pattern. The pattern is the proactive pattern. It may not suit every application, but if you're using this pattern, Boost.Asio is an excellent choice. So a few words about Boost.Asio, because my examples will use it. It provides a wrapper for synchronous and asynchronous use of sockets and other operating system objects. And it shines when you want to use the asynchronous I/O. You have the central object that you want to use with Boost.Asio is the I/O service. Every object that you want to use, every operating system object is represented by a wrapper which takes a reference to an I/O service. It's the central part of the mechanism. And the I/O service has inside it a event loop, let's say a queue of work. The queue of work can be dispatched by a call to I/O service run. And every time I/O service run is called, it looks at the event queue, it detects if there's something to do, and if it does, it invokes it. It doesn't know what it's invoking, it's a callable object, it invokes it. That could be the output of a callback. It could be a callback that's being invoked. Usually it'll be a callback, but under the hood, that callback could be doing many things. Boost.Asio is not aware of that. And when there's no more work to be done, I/O run exits. As long as there's work that's being posted back to the event queue, I/O run continues to work. And it should be said that asynchronous APIs can have many different overloads. Chris Kolov, the author of this library, has provided a generalized way to invoke asynchronous operations. So what may look like a simple operation like async read on a socket can actually be overloaded in many ways. It can be overloaded, the simple overload is one that takes a callback, and Boost.Asio then calls the callback when the completion is complete, when the operation is complete. But there are other ways of invoking an asynchronous operation. You can provide a tag which tells Boost.Asio, please return a future object representing the result of this asynchronous operation. Now that's supported by the library. And future objects are very important because future objects allow us to await, to co-await. So the example I want to show here, a very simple example, demonstrates how we can use Boost.Asio and Coroutines TS. Coroutines TS will work seamlessly with Boost.Asio for its asynchronous API. Okay, so here we have a very simple function. Let's look at the main. The main function creates an object of type IO service, and then it performs sleep and then IO run. This function sleepy returns immediately. It may not be obvious at the moment, but it returns immediately, and immediately the main function goes into IO run and starts servicing the loop. What's happening inside that event queue? Or if you look inside this operation, this function, you will see that there are a number of co-awaits. Each of these co-awaits is calling an asynchronous operation. This is a timer object. I want you to ignore for one moment the first line of that function. This is the detail of Boost.Asio, which I don't want to go into now. But the second line creates a timer, a system timer, which is based on Boost.Asio. The timer is associated with the IO service, so it can post callbacks to the IO service. And then we can configure the timer to trigger in 1 second. And then we can co-await on the async await function. What's happening here behind the scenes? Well, there are actually two, I would say, general specializations that are happening. First of all, when you specify this particular tag, Boost.Asio use future, to an async operation in Boost.Asio, miraculously, the overload that is being called within the Boost.Asio library is an overload that returns a future. And the type of the future is actually deduced from the other parameters. But for the moment, we're talking about a function that takes no other parameter, returns no other parameters, and therefore what is returned is a future void. The second specialization is that the Coroutine TS, which is a very low-level implementation, actually provides wrappers for some common usage patterns, one of them being functions that return futures. So there is an appropriate specialization of the coroutine that allows you to co-await on a function that returns a future. So these two are working together here to make the asynchronous call to the timer callback appear to be a synchronous call. Because immediately after the co-await, it looks as though we're continuing, but what actually is happening is we are returning immediately back to the main loop. The main loop is invoking IO run, which inside the Boost.Asio library is checking for work to be done. Well, there is work to be done because we've just scheduled a timer to go off in a second. When that eventually does get called, the callable object will be invoked. The callable object that will be invoked is the callable object provided by the Coroutine TS, and the Coroutine TS sets the future. Eventually, returning the control to the function that was originally instantiated, the coroutine. So then control continues to the next section of the code. It makes a print, and then it does another co-await. And each of these co-awaits does the same. It provides work to the Boost.Asio, asynchronous work to the Boost.Asio, and suspends. Control is returned to the loop. The loop, the IO service run, continues to look for work. When it finds the work, it executes that work, which resumes the coroutine at the point of suspension. So what I want to take away from this particular example is simply that through specialization of Boost.Asio and the specialization that is provided for us by the Coroutine TS implementation in Visual Studio, we can use Boost.Asio in a synchronous way, even though what is actually occurring is asynchronous. You may ask, where are all the threads in this? I think it's important to mention that in this case, this is a very simple ASIO application where there is only one main thread and IO run is being run on that thread. But in a generalized situation, you can have many threads being instantiated and blocking on calls to IO run. And any of those IO run invocations may be the one that picks up the result of this timer or any other asynchronous operation, calls the invocation and invokes the resume of this function. So you need to be aware of the fact that the actual thread that is running the code may not necessarily be the thread that instantiated it if you're running an application that instantiates many threads and calls IO service run from each of them. This is entirely under your control, but you need to be aware of it when you re-enter the coroutine. Okay, so at this point, what I'd like to summarize and say is that we've talked about patterns for using coroutines, and I've touched upon the implications of the differences between the two implementations of which we are aware. One, which is the Coroutine TS, which is in the process of standardization, and the other is a library, the Boost Coroutine 2, which I've shown you again through example. Are there any questions about this? Okay, so let's go forward and talk about asynchronous IO, threads and fibers. To demonstrate how these work together or how they contrast, I prepared a sample which actually is made up of 4 separate projects. The names are unimportant, they will become clear as I move through the examples. But basically we have, in this sample, we have an echo server and an echo client. The application actually is one application, it creates threads for each of the clients, and what they do is they connect to the server, they send some information, and the server sends back exactly the same information that was sent. Both of these objects, the client and the server, echo what they receive from the server or what they receive from the client. So it's a very simple application. Clients are instantiated, and they start a conversation where they ping-pong data with the client, with the server. Underneath the hood, there is a message object. And the message object, I have intentionally made a little bit complex. It has 2 parts to it. It has a header and it has data, payload. In order to read a message, you need to make 2 IO calls. You first need to read 8 bytes, size t, giving you the size of the data. And then you need to read the amount of data specified by that size t. This will become important later on. It complicates things a little bit when reading from the stream. So I want to zoom in on the messenger object and show you how that messenger object would look like in each of the different technologies that we can discuss for I/O in this case. So the first one, called Yosync Threads, doesn't really use Boost.Asio for asynchronous APIs. It's just a simple blocking API. But in order to be a little bit more efficient and to be more responsive to connections, the connection runs in its own, the server runs in its own thread. And every time a connection comes, it listens for a socket to connect. And when that socket connects, it creates a connection object and spawns the connection object in a separate thread. That separate thread runs with simple synchronous calls using Boost.Asio. What's good about this? Okay, here's the code. The messenger read and the messenger write would look similar. Makes two calls. One to a read of the header of size t. Then it creates a message of that size, and then it invokes Boost.Asio again to make another synchronous call to provide the data. If you're wondering where the error handling is here, implicitly in these calls, if you do not provide a placeholder to get back the error code, these overloads that I'm using here will actually throw an exception, and if that's handled elsewhere, we are fine with this implementation. It's simple asynchronous code. Synchronous code. What's good about this? Well, the good thing is the main thread can continue to be responsive to new connections because all of those synchronous calls are occurring in a thread. The bad thing is that creating a thread is expensive, context switching is expensive, and expensive not only in allocation of stacks, but also in the time it takes to perform a context switch. I'll show you later on a quick slide from the Boost documentation, Boost Fiber documentation, that points out that context switching in fibers can be, not always, but can be 3 orders of magnitude faster than context switching among threads. So we like to, I would say that if you're only having a few threads, that's fine, but as soon as you have a large number of threads and you want to scale up, it can be practically impossible to manage that amount. The context switching will actually dominate, even if you're able to create the threads, the context switching will dominate the operation of the server. So it's good and it's bad. So what we'd prefer to do is to do asynchronous I/O. Now we have Boost.Asio. We're using Boost.Asio, so Boost.Asio gives us this support. What we want to do is use the completion handler to get a callback and then leave immediately to do more important things. Now, it does fit on the slide in this special case, but this code is very confusing. This is a relatively simple asynchronous call invocation of a read, reading the message that I need, using Boost Asynchronous IO. Now, who can tell me what is the first actual IO function that is being invoked here? Where is it? At the bottom. The next piece of code, after I've instantiated that function, I've initiated the function, occurs in the callback, which actually is up at the top. Here is the callback at the top. It then decides whether the read was successful, and if it does, then it continues to the next call. Where is the second piece of code that gets executed? Somewhere in the middle, the async read, somewhere in the middle. And where do we finally end up? Right in the bang in the middle, where it says, just next to the title, reading a message. There you see is the final handler, which does the completion, and it moves the message out of this callback into the caller, into the handler, sorry. So it's very convoluted. Now, a good code review and extensive testing will help you here. But of course, it's difficult to manage. What we would like to do is we would like to eliminate those callbacks. Okay, so the good is, again, we have the main thread is responsive, and it scales well. By the way, in this application, why do I say it scales well? Because if we're using Boost.Asio, we're not creating a connection, a thread for every connection. In fact, all we're doing is we're spawning coroutines. Sorry, all we're doing is we're spawning asynchronous operations. Each of those asynchronous operations then gets posted to the event queue. And what actually is working on threads is the IO service run. The IO service run, which is called elsewhere, is the one that is running in a thread and is handling our connections. And depending on how many times you called IO service run on your thread pool, that is the amount of threads you're actually working with. So you can actually separate your decoupling, the number of threads that you use for servicing your queue, and the number of connections. You can be doing any number of connections without creating more threads. So asynchronous IO is efficient in this way, and it scales well. However, callback code is difficult to manage. Enter coroutines. What I'm demonstrating here is a simple example of integrating Boost coroutine with Boost.Asio. And a similar demonstration could be made using the Coroutine TS. I just chose to use this one because it's less well known. The Coroutine TS we've already shown is compatible with asynchronous operations that are capable of returning a future. And Boost.Asio is such an asynchronous API. So whatever I can show here, we could also show using the Coroutine TS with some modifications. Another important point that needs to be mentioned, when you're using Boost.Asio, you're using callbacks. When you use callbacks, the object that is being called back upon must be ensured to be alive. If it's not alive, if it's been destroyed, then of course we get an access violation. So in order to be able to use Boost.Asio correctly, you need to be able to use shared pointers efficiently. Shared pointers extend, using enable from this, shared from this. You can extend the lifetime of the object that is being called back to make sure that when the callback arrives, the object is still there to service it. So that's what you see here. What you see here is just the general pattern of creating an instance of myself from a pointer to myself, a shared pointer to myself from a pointer to myself, and passing that in to my my business logic. Okay? And the second thing, but this is actually new because I'm using coroutines, is the spawn function. The spawn function is specifically for use with coroutines. This function reminds us in a way of the way we created the generator with Boost coroutines. If you remember with the generator, we provided a lambda, and there was an implicit push type that was created for us that we could use for the context switching. That's been wrapped in Boost.Asio with a yield context. It represents that push type. And it's implicitly created for us, and we can then use it and pass it into our business logic. Our business logic is all inside the start operation, which accepts, in this case by value, that yield object. That's the first part. The second part actually looks very much like the synchronous code. Here is an asynchronous implementation using coroutines, very much like the synchronous code. Who can spot the difference between this and synchronous code some slides back? There's the yielding callback, exactly. Well, actually, there are two differences. One is that I'm actually using async read as opposed to read. And the second is that the last parameter is a yield object. Now, what that means is an implementation detail. There is an overload in Boost.Asio that accepts this yield object. It is, in fact, a wrapper object created by Boost.Asio for this purpose. And internally, there is that push type that does the context switching for our coroutine. So what this async read is actually doing is suspending the call to async read internally, inside that call, and scheduling a callback based upon that yield object. When the callback returns, it is posted to the Boost.Asio event queue, which eventually gets serviced by one of the calls to run, which then wakes up the coroutine and continues to run from that point onwards. So we have our inversion of control. We have something that looks like a generator, in fact, but it actually is an asynchronous call, as you can see. And it's very simple to manage. I make two calls, one after the other, code is sequential, state is preserved, and I could nest this deep under into my application. It would look like synchronous code. Okay? And as I said, I could make a similar change to use the Coroutine TS for this operation. It would require, of course, that all of my functions would themselves need to be coroutines, but this is my code. I can do what I like. Okay, so what do we have here? We have all the good advantages of a responsive API, an API that scales well, an implementation that scales well because I'm not generating a connection for every object. A thread for every connection. And now the code is organized like synchronous code. Okay, I want to make a short detour now and talk about the Boost library. This is, in fact, what we came to listen about. So I want to talk about the Boost Fiber library. And really, it's an overview. I really recommend you look into the documentation. It's very well documented and easy to read. And also, it should sound very similar because the semantics do remind us of the threads. So a fiber is a userland thread. It is a thread of execution that is scheduled cooperatively. That is the difference between a fiber, the main difference between a fiber and a thread. The library is organized as coroutines based on Boost context, plus a manager, plus a scheduler. Each fiber has its own stack. And underneath, there is a boost context. Every fiber has a stack created for it, and there is the capability of context switching between the stacks. There is a problem here, which is often reported to be a big problem, the fact that we have to allocate stacks. But I do want to point out that as for the case of coroutines, the boost context does provide an API to allow you to customize the stack allocation strategy. So you can decide on the size of the stack, and you can also decide on other allocation strategies. So, fibers that are created on a particular thread generally run on the same thread. So if you have two fibers created on the same thread, they will not conflict, they will not need protection against use of a common resource. Of course, if you're cooperating with fibers from different threads, all bets are off. You need to make sure that those threads, those fibers on behalf of those threads, do not collide in use of a resource. The library is based upon a manager, okay? The fiber can decide to yield itself cooperatively, and then it invokes the manager. And it says to the manager, I've got nothing to do, or I want to give someone else a chance to do something, yield to another fiber. What the manager does is it consults with the scheduler, whose job is to look around for any other ready fiber on this thread, and then decide which one is the one that needs to be run, and then pass control, switch control to that fiber. There aren't two context switches here. There is only one context switch. The original fiber calls the fiber manager. The fiber manager consults with the scheduler, which decides which fiber to run, and then it makes the function to context switch to that fiber. The context switching is direct. The scheduler algorithm itself has a default. The default is a round-robin scheduler. So it generally tries to treat all the fibers in the thread fairly. But you can decide on the scheduler algorithm yourself. You can implement your own, and you can use some of the other options that are provided with the library. So for instance, if you want to associate a priority with certain fibers, you can do so. And this is completely customizable. What I would like to show you is how fibers suspend, because here's an essential difference between fibers and threads. Fibers can suspend in, let's say, one of two ways. They can sleep. There is a static function, just like with a stood thread. You can stood this thread, sleep. You can do the same with fibers. Boost fibers, this fiber, sleep. And you have a sleep and you have a sleep for. Very similar to the thread API. But you can also use fiber synchronization objects to suspend. Mutexes, I'll just show you a list of those in a moment, mutexes and conditional variables and so on. The important thing to remember about these fiber synchronization objects is that they do not necessarily block the thread. All they do is suspend control, and they tell the scheduler, look, or the manager, look, I've got nothing to do. I have to wait for something. So here I'm going to go to sleep, meaning I want to be suspended, I want to be ready. Go ahead and consult the scheduler for a different fiber that should run. The scheduler will then look for all of those that are ready. Now, depending on what exactly the fiber requested, the fiber that made the call may in fact be the one that is selected. If it just yields, then it remains ready, and it just gives a chance for someone else to get a chance to be called. If there's only one thread, only one fiber, then it will itself be called again, immediately. It's a no-op. But if it made a suspension call, it says, I don't want to be ready. I will be awoken at some later time, and meanwhile give someone else the chance to run. So these are the synchronization objects that you have within the fiber library. You have mutexes that are all with the right namespace, as you can see. Conditional variables, barriers, future promise package task, as you might expect. And you also have a buffered channel and unbuffered channel, which behave, if you like a future. Two sides of a future, and two sides of this are like a future and a promise. But instead of generating one value, they generate a sequence of values. And again, what's important to understand is that these do not block the thread. There is, of course, one caveat. If there are no ready fibers, if all of the fibers have gone to sleep, or all of the fibers have yielded to some synchronization object, then the synchronizer will say, the scheduler will say, I've got nothing to give you. I'll give you a null fiber. And the manager will say, oh, nothing to run, we block the thread. And that can, of course, be woken up as soon as some fiber becomes ready. As I mentioned before, context switching is fast. You can look at these numbers in more detail on the Boost Fiber documentation, but you can see here two numbers that I wanted to point out, is that in this particular run, the stood thread context switching was in the order of 52 microseconds, whereas the fiber, optimized with the work stealing algorithm, is 3 orders of magnitude faster. So this is the real benefit. How do you use a fiber? You invoke the constructor of a fiber just like you would invoke the constructor of a thread. The one difference that you see here is that there's an additional parameter which is optional, which tells the fiber manager whether to immediately resume this particular fiber. That would be a post launch value, or to put it on the ready queue and then allow a yield from another fiber to enable this one to run. This is an example of a use of an unbuffered channel. I won't go into it in too much detail, but what you can see here is that both the push and the pop suspend the fiber. And here again, and this is really what I wanted to come to, is how you can use futures and promises. Here is an example of an asynchronous call to Boost.Asio, which is a blocking call. It would look like a blocking call. Here you have a promise of an error code, and from that promise I create a future. And then in the callback to my read function, I set the value. I could also set the exception of that promise. And then what does our function go and do? It goes and calls future.get. This is a blocking call. We're used to thinking of these as bad ideas. This would require a context switch. But in the context of Boost Fiber, it doesn't block the thread. What's happening here is that the fiber becomes suspended. And immediately, the scheduler gets the opportunity to select a different fiber, which may be ready and have work to do, to work instead. From the thread point of view, the controller is just moving from one function to the other. There is no entry to the kernel, and there is no unnecessary blocking within the kernel. Yeah.
So for this to work, the I/O service run has to be a fiber as well, right?
Yes. That's an important point. I won't go into that in too much detail, but if you look at the documentation for fiber documentation, there is a suggested implementation of a specific scheduler, which does what you say. It calls both IO service run and the yield to allow both fibers to run and IO service to run. So in the final part of this demonstration, which, as I said, you can take from the link that I gave you earlier, here is a new messenger read, a function which would seem to be a synchronous function. It blocks, but it's fiber friendly. It only blocks the current fiber. Any other fiber can continue to run. So if you like, internally, what's happening is, this is like a coroutine. There is a suspension and then a resumption. So the good with a fiber implementation is you get all the advantages of the threadless option. Right? You don't create threads per connection, you create fibers per connection. And the only thing you have to manage, as was pointed out here, you have to make sure that fiber yield is called at some point in your scheduler. Okay, that's a small point which I recommend you look at the documentation to get more information about. Okay, one final comment about fibers as opposed to coroutines. In the specific example of Boost.Asio, this is really a continuation of what you're saying. You'll recall that I mentioned that the fiber library actually is coroutines plus a scheduler plus a manager. This manager conflicts a little bit with Boost.Asio. Boost.Asio already has a manager. One is managing the queue inside the IO service, and the other is managing, the fiber manager is managing the queue of ready objects inside the fiber manager. And therefore, some adaptation is required to make sure that both of those are called in the right place. So the ideal situation to use a fiber as opposed to a coroutine is where you yourself are in control of the main loop. If you yourself have your own main loop and you're handling the asynchronous operations, all you need to do is to intersperse your calls with yield from time to time to make sure, and you can fine-tune that, to make sure that the fiber library gets the opportunity to reschedule new fibers. Okay? Questions?
Will the fiber synchronization objects do the right thing for different threads? So like if I have a Mutex, a fiber Mutex, and I block on it from one fiber and from another fiber on a different thread, does it do the right thing?
So I'm trying to understand, you're using fiber Mutex from two different fibers.
On different threads.
On different threads. Okay. This depends on which scheduler you're using. The default scheduler is a round-robin scheduler which operates in the context of one thread. So the Mutex will suspend this fiber and yield to any other fiber on the same thread. It will not have any effect. It will not do what you expect it to do for the fibers running in another thread. Okay?
But not like log.
No, you would have to protect yourself with the thread synchronization objects. Okay? So in other words, the answer to this basically is you're still running in the context of a thread. As long as you're running in the context of a thread, you don't need to use thread mutex. You only can use the fiber mutex. But if you're running in separate threads, then you're back in threadland. You have to protect yourself accordingly. Yes?
Coming back to your use case where you implement fiber for SIX parser and
Yes.
yield from there. I mean, from my experience in general, one of the challenges of using the approach of just converting a random library into a kind of coroutine, using in coroutine with fibers, is that you essentially fibers break thread local storage. And it happens often, actually. Even with runtime library, it happens. So what was your experience?
So you're saying that from your experience with fibers break in some way the use of thread local storage?
What I'm saying, if you call a library
Yes.
which take dependency on the thread local storage, let's say it sets something and then later on it expects to the value be there, that the fact that it's actually in the context of fiber and it could get moved from one thread to another thread, the value will change in the middle.
Okay, so I understand your point. What you're saying is that because fibers can migrate from one thread to the other,
Right.
there might be a problem with thread local storage. So I think the correct answer to that is that by default, fibers do not migrate from one thread to the other. The scheduler, which is an extension point, the default scheduler is a round-robin scheduler among fibers of the same thread. So when fiber yields, it yields to another fiber in the same thread, and therefore they can access thread local storage without any problem. There are schedulers that will allow you to migrate fibers from one scheduler, that they can still work from other threads.
Right.
When you do that, you have to manage, for instance, thread local storage will be a problem because you have to make sure that it is protected.
Right, but even...
that it's accessible.
Even there, you have to be careful because if you, let's say, schedule another fiber which could change thread local storage and then restore back, it still might be a surprise. So essentially, you need certain guarantees from the libraries. You need to make sure.
But I don't think that's a problem because all of the coroutine, all of the fibers running in the same thread are just like functions running in the same thread. It's like saying that two functions in a thread might modify.
Well, what I'm saying, the library today might work. Once you put it in a fiber environment, all suddenly you will find surprises.
Okay, what I suggest you have a look at, I mean, maybe you've already seen,
I
is to
experimented
look at the options to customize the scheduler algorithm. As long as your scheduler algorithm does not migrate fibers to different threads.
No, it's still not enough. I mean, not all the cases. It will solve some.
Okay, well, maybe come to me afterwards and we'll discuss that a bit further. Okay. Yes.
Hi, I want to warn about use future, as you had on your earlier slide. Coroutine TS provides just raw language changes.
Right.
The freebies of being able to await on the future are the things we put together in Visual Studio so that people can play, but in no way, please do not use them in production, because if you look at the implementation, there is no feature to then. So what it does, it launches a thread and then does blocking.get. So do not use it in production. Moreover, in Clang, it will not work because it is strictly doing the TS, and thus you will not have a waiting on the future. But there will be a talk this week where we will show how to use IO and coroutines very efficiently. So.
Okay, thank you. So may I just rephrase that to make sure I understood? What Gore is saying is that the coroutines TS is basically a low-level API which allows library authors to use for their own purposes. And one particular use is the one that is implemented today by Microsoft for future returning functions that return futures. And as you've probably seen in the implementation, I looked at that implementation, it does rely on the ability to attach a then to the future. So as long as you're using the experimental APIs that Microsoft have been using here, then that's fine. But if you don't have the then it won't necessarily work, it'll block.
Well, in this case, I use stood future, which is not in the experimental namespace, which does not have .then.
Right.
And it has very inefficient way of awaiting on it. So if you take this example and run it, performance would be horrifying. But
so I need to use stood experimental future, is that correct?
use Boost Future and
Boost Future.
use Boost Future
Or
and
Boost Future.
use create an equivalent of use_future that is defined by, I think, Boost.Asio that does the equivalent for the Boost Future.
Right, thank you.
Performance will still not be good, but it will be better.
Thank you very much. Any other questions?
I was curious, how much overhead was there from context switching between the stacks on Boost Coroutine 2?
So, as I mentioned on the slide, there is an overhead, but it should be efficient as more or less like a function call. The context switching is very fast. It doesn't require an entry into the kernel. So that, I think, is the most important gain.
Was there a study how much actually effect fibers have on the committed memory of the process as the stack of the fibers getting committed? And if fibers are long-living?
I'm not aware of those. The question is about stack allocation algorithms. I'm personally not aware of those. I've been using the default, which is the fixed stack algorithm. But as I'm sure you are aware, there are ways that you can customize that. And I'm not aware of the studies that have been done. You might want to contact Nat or Oliver and give you more information about that.
Okay, thank you.
Okay. Okay, maybe one more question and a quick summary.
Is there any alternative for Python yield from when you can propagate result of nested coroutine to the caller of your current coroutine?
Well, actually, Gore mentioned earlier, you're referring to the coroutine TS.
Yeah.
Yeah. Maybe Gore can answer that for us, because he did mention earlier that it's possible.
So first, yield is an expression, not a statement. So if your library so desire, you can implement the coroutine, which for some reason would be yielding something back, kind of like a request reply. Second, if you want to yield from nested, there are several techniques. One of them use like channels in Go, and you pass the channel to whomever you want, and then when he pushes the value into the channel, you can consume it in some very far remote coroutine. Or there are several open source libraries that support coroutines, and they have recursive generators where you can yield a result of another generator in one go. You don't have to spin the loop and extract, and it's very efficient.
Right. So in other words, when you're using a channel of some sort, like for instance the fiber channel, then basically you're converting the co-yield expression to an object that can be passed around.
Yes.
And then anyone can then push to it, just like they push to a push type in coroutines.
Right, but if you want to suspend while it is being processed, that has to be a coroutine.
Right.
Yeah.
Exactly. Okay. Okay. Maybe one more question?
It'll be really quick. It's a statement. Even if you're not using MSVC, there's at least one third-party library that provides an implementation of generator T. So Louis S. Baker on GitHub.
Okay. Using the coroutine TS.
Yeah, and supplies another generator and a bunch of other primitives. So.
Okay, thank you very much. Sure. So to summarize, I do want to point out what we've done actually, we've just talked about coroutines and the usages for coroutines. We talked about generators and about parsers and about asynchronous IO. The general idea here is that you see an inversion of control pattern. Then we talked about asynchronous operations using threads and the benefits of that, but also the problems related to threads. And what I've proposed here is the ability to use fibers where you would otherwise use threads. So I hope I've convinced you that it's a good idea to take a look at the fiber library, the Boost fiber library, and you will discover that in many cases, the use of fibers will boost the performance of your programs if you use them in addition to coroutines. Thank you very much.